So Jupiter, what's the big deal? Well, we've got all these storms and more storms. Yep, a bunch of storms. Well, why all these storms? And why do these gigantic storms tend to happen on gas giants? To truly understand, just take 10 seconds to give this video a like and subscribe. So let's get into this. We'll be covering 5 different things. Number 1, what's a gas giant? 2, the Coriolis effect. 3, Jupiter versus Earth. 4, what powers the wind? And finally, the big red spot. What's a gas giant? Most of us already have a basic idea of what a gas giant is, so let's get through this quickly. A gas giant is a particularly large planet made mainly out of gases. Because they're made out of gas, they have a very low density. For example, the planet Saturn, aka the second best planet, the best planet's Earth. So Saturn has such a small density that it could actually float on water. Now you may be wondering, what's all this talk about supermassive gas giants if they could float on water? Mass and density aren't exactly the same. You can see that Jupiter is extremely massive, but it's gigantic. If Jupiter was about the size of Earth, all of this matter would be so tightly packed that the density would be extreme. Possibly even so dense it wouldn't be able to sustain itself. So next up, the Coriolis effect. What is it? Why does it matter? Is it even a thing? First, yes, it is a thing. If it wasn't for the Coriolis effect, every possible storm would collapse the very moment it starts. The Coriolis effect is basically the rotation of a planet causing storms to rotate. But let's look at it in more depth. If you take a paper airplane and throw straight north from, let's say, Sacramento, California, you might expect it to land somewhere around Klamath Lake, Oregon. That's if you have a very strong arm. But if you could send it flying that far, it would probably end up somewhere in Riddle, Idaho. Since the Earth rotates in a clockwise direction, or in our case, east to west, things being tossed around like this move slightly to the east. Now with the storms, this concept exists in the same way, but the one thing we do need to account for is that the equator rotates faster than the poles. Or another way to see it is when you spin a fidget spinner, the arms, or like the little parts that are spinning around that make that spinning view, cover more distance in a single rotation than the part of it right next to the handles. This causes all the wind circling the storm to rotate instead of collapsing right to the center. It also causes storms in the southern hemisphere to rotate clockwise and storms in the northern hemisphere to rotate counterclockwise. Jupiter versus Earth. Less about who would win, but more about the differences and similarities. Sorry to ruin your excitement, but it's life. So to start with, both Jupiter and Earth have a Coriolis effect. But on Jupiter, it's extremely strong, both because of its 10-hour days, but also because of its extreme size. Not only does this gigantic effect cause the storms to be stronger, but the storms also last longer. And with no continents to disrupt these storms, you can see why this red spot has been there for so long. Now, by what you know, you probably wouldn't expect a gang of storms at the poles on Earth. But in Jupiter, we have some different activity up there. Up at the poles, we have one big storm with a bunch of other storms circling it. This is a slightly new discovery, so we don't know much about it. But what we do know is that there are small buffer zones that rotate in the opposite directions as the other storms, but also make it harder for the storms to merge and easier for more storms to join. So you may be wondering how we get these 250 mile-per-hour winds on Jupiter. Well, I can say for sure it's very similar to wind and storms on Earth. Jupiter has layers in its atmosphere. The outermost thinnest layer, the exosphere, containing mainly hydrogen and helium, leaking out a ton of gas particles because it's right next to outer space. thermosphere, not leaking out anything since it's low deeper in the planet. It also contains hydrogen and helium. The stratosphere, containing hydrocarbons. As you can notice, the chemicals in this layer start to get a bit heavier. And lastly, the lowest, deepest atmospheric layer in Jupiter, the troposphere, containing ammonia, a few other ammonia mixtures, and water. Yes, you heard me correct, water. The production of these wind and storms starts with the water in the troposphere turning into water vapor. Then, as the water vapor rises, it causes a strong upward force causing all the wind and storms. As little accessory, convection, which is heat transfer through liquids, convection in the water and water vapor makes lightning. And, as you might expect because of the ammonia, there's a possibility of acid rain. So here you have it. Intense. Section will be about the most intense storm in our solar system, the big red spot. Now, how did it get so red? This is due to its ammonia-filled clouds and extreme sun radiation to that area. Since it's a lot bigger and older, there's more area for the sun to heat, and it's had a longer time to get this red. You might be wondering how it got so big. Well, we don't exactly know the full history of it, so we don't exactly know how it got so big. But if I were to guess, I would say because of the swallowing of other storms. What might seem astonishing about this storm is that it's actually shrinking and getting taller, making it really unstable and putting it at a risk of getting torn apart by really strong winds. Finally, the age of this storm. Like I said earlier, we don't really know the history of this storm, but we do have estimates ranging from 300 to 400. So if you were asked this question, just know that we don't know for sure. So thanks for watching my video. Again, make sure to give this video a like and subscribe. To learn more, go to Cosmos, the Science of Everything. See you around!